Okay, so we were talking about curves, in particular about divisors on curves. So again, C is a curve, which means a projective, very smooth projective curve. Dimension 1. And as I said, the divisor on C is a formal sum of the form D equal to sum P in C, AP times P, where the AP are integers, and only finite dimensions are non-zero. And these form a group just by adding the coefficients and subtracting them and so on. The zero element obviously is the zero divisor where all the coefficients are zero. Then, so just we have these words, a divisor is called effective if all these numbers are non-negative, and we have the support of the divisor. This is the set of all points where the AP is non-zero, and there are a few more such words, and the degree of the divisor is the sum of these coefficients, which is some integer. Okay, and then we had defined the divisor,
Sorry, there is a silly question. Why it is called the divisor?
I mean, I don't know precisely, but if you I don't know historically what the reason is, but if you well, I want to say something, but I think it's not true. So so I mean the answer is I don't know. Okay, I mean I wanted to make some conjecture, but it seems to be false, and so I really don't know. One must look it up. This must be, but I do not know. Okay, so that's so if for H a rational function, we can define the divisor of H. This was just the sum over all the points in C of the multiplicity at P of H times the point P. So we have a divisor associated to a rational function. And this is the divisor. And obviously we have that the divisor of the product is the divisor G plus the divisor of H. So we get that divisors form a subgroup. So a divisor of this form is called the principal divisor. And the principal divisors form a subgroup. Of the divisors on C. And furthermore, we introduced the linear equivalence. So divisors D and E are called linearly equivalent if and only if the difference D minus E is a principal divisor. So therefore and we call the Picard group of C will be the divisors of C divided by this linear equivalence. So this is also the group because we have divided by a subgroup. So then we had introduced the degree of homomorphism. So if P from X to C is a dominant morphism of curves, actually if it's not dominant, the degree will be 0, but anyway, of curves, then we have seen that Kx over Kc is a finite field extension. Because it is both are finitely generated field extensions of K, and both have transcendence degree 1. So it means that Kx, so it means every element of Kx is algebraic over Kc, and there are only, we can obtain Kx from Kc by adding finitely many elements, so it's a finite field extension. And so the degree of T is defined to be the degree of this field extension. And so now we wanted to define the pullback of divisors by morphisms and show that it multiplies the degree of the divisor by the degree of the morphism. So the definition. So let so again phi from X to C be a dominant morphism of curves. So we define as follows. We want to define a homomorphism C star from the divisors of C to the divisors of X, which we can think of as pullback of divisors, as follows. First we say what the pullback of just the divisor consisting of one point of multiplicity 1 is, and then we extend by linearity. So for Q and C, we have so obviously the fiber over this point must be finite, otherwise everything would be mapped to this point. So we have that phi to the minus 1 of Q is some finite set, when P1 to PR. So at each point, so let T be uniform parameter at Q, a uniformizing parameter at Q. Then obviously if I take the pullback of this uniformizing parameter, which by definition is, you remember, is just T composed with phi, this is a regular function. This is regular at all these points, and in fact, as this function vanishes at Q, it is 0 at all these points. It vanishes at all these points. It's in the maximal ideal. So this is, so if I take this is an element in the maximal ideal at Pi, so M Pi, for all I equals 1 to R, because the function vanishes at T, so if I compose it, it vanishes on all the points of the English image of T. And so, thus, we define phi star of the divisor of this divisor Q to be sum from I, and maybe want a bit more, want to squeeze it like that. The sum, so phi star of q is defined to be the sum over all the points in the pre-image, I and 1 to R. We take this pullback of phi of this function, and we take its multiplicity at pi times pi. So this will be a divisor on x. And note that these multiplicities will all be positive. So it follows that phi star q is an effective divisor with support. No, just the inverse image, phi to the minus 1 of q. So it resides PR1 to PR. It's when, it is non-zero at all these points and the coefficients are positive. And then I said for general divisor, we define the pullback by linearity. So one should check, just I will say, so you have to take a uniformizing parameter. If I take another uniformizing parameter, it's obtained from t by multiplying by a unit. So this unit is non-zero at the point q. So I multiply everything by a function which is not zero there, and the result doesn't change. No, the order of vanishes.
Just why is it this effect? Why are these all coefficients non-zero? Why
Well,
are they positive? Why?
I mean, I said it a couple of times, but let me say it another time. So this function t vanishes at q.
Yes.
The pullback here is just a composition with phi. So if phi maps pi to q, t vanishes at q, so t composed with phi vanishes at all points in the inverse image of and at all the pi. And if it vanishes, it means it lies in the maximum ideal, so the multiplicity is positive.
Yeah.
Okay, it's just okay. So this is an effective divisor, and so where was I? So extend by linearity. So if d equal to sum ai pi minus sum just sum ai pi is I just say a q whatever ap times p is a divisor in C. We put phi star of d equal to the sum over all p in C ap times the pullback of p. No, this is just to make it linear. So it's an easy exercise which tests whether you understand this definition. So if f is a rational function, then the pullback of the divisor of f is the divisor of the pullback of f. It follows directly from the definition if you kind of unwrap it. Okay. So maybe if it's not obvious, you should try it. So okay. So thus in particular we get the remark. So again we have phi this dominant morphism of course here still. Then if d is linear equivalent to E, so it follows from this, as divisors on C, then it follows by this exercise that the pullback of D is linear equivalent to the pullback of E. Namely, if there's an F whose divisor is the difference between these two, then the pullback of F will be the difference between these two. So therefore, thus we get, thus if I pull back the linear equivalence class, so D, so if I take phi star from the Picard group of C to the Picard group of X, which maps the linear equivalence class of the divisor to the linear equivalence class of the pullback of the divisor, this is, this is well defined by this, and it is a group homomorphism. And in fact, you can see that if you take the inverse, it will give you the inverse of the pullback, and so it will follow that if X and Y are isomorphic, then the Picard groups are isomorphic. So this is an invariant which is associated with the curve, which is actually quite counterintuitive. Now we want to see one thing. So I want to use now a theorem which I don't have the time to prove, which is it's not particularly difficult, but it would take quite a while to do it, and this requires some algebra. And so I will just state it without any kind of fake proof or something. So the theorem, and so this is that this pullback is somehow compatible with the degree of divisors and morphisms. So the statement is so if let P from X to Y, X to C be a dominant morphism of curves, then the degree of the pullback of a divisor is equal to the degree of the morphism times the degree of the divisor. Okay, so it's a very key thing. So, so in particular, one should notice, so in particular, this is maybe a remark. In particular, so if Q in C is a point, then so the degree of phi star of Q is equal to the degree of phi. So that you could interpret as saying that the inverse image of any point consists of degree phi points if one counts them with multiplicities. So the multiplicity being this multiplicity here. And if our field has characteristic 0, one can actually show, but we don't, that for such a dominant morphism, actually there are, for a general point, Q in C, these multiplicities will all be 1. So in that case, it would follow therefore that for a general point Q in C, the number of points in the inverse image of Q is precisely the degree of phi. So the degree really means the number of points in the inverse image of a general point. So this, but I mean the second statement is only true in characteristic 0. Otherwise you have things like the Frobenius morphism or something which don't do this. Okay, so I will not try to prove it. So And now I want to deduce from this that principal divisors have degree 0.
Is that related to Bezoar theorem? Or Bezoar, I don't know.
Yeah. So, I mean, I will. So, one can build up things in different ways. For instance, you could somehow prove by elementary means Bezoar's theorem, and then you could use this to somehow prove these things, and in particular prove that principal divisors have degree 0. And we kind of take the opposite approach. We kind of use this theorem, which one can also prove directly by. It then comes in some sense a statement of algebra. And then Bezoar's theorem, as we shall see, is a consequence.
So this can be proven without Bezoar theorem?
Yeah. Yeah. So if you look in Hartshorn's book, which maybe is not the most elementary source, but anyway, there's a completely algebraic proof of that. And I think that if you look at Schafarevich, there's also some direct proof just by. But on the other hand, if you look in Fulton's book, this is a consequence of Bezoar's theorem. Okay, it just depends on how you want to build things up. So principal divisors have degree 0. So proof. So let f be a rational function. So obviously, if you want the corresponding divisor, must be non-zero rational function. So if f is constant, then it vanishes nowhere. So then the divisor of f is 0. So that's okay. And so let's assume now that f is not constant. So if f is not is an element in K C without K, then I claim that f defines a morphism. Actually, it defines a dominant morphism. Which I now call it phi, which is equal to 1 comma f from C to P1. So these are both rational functions, and this defines me here a rational function. We anyway know it can be extended to morphism by a theorem as before, but we will actually need explicit extension anyway. And it's certainly dominant, because dominant means that the image is dense, and the image is dense for a curve just means that the image is not just one point. And certainly that we have just excluded. Okay. And then we know that if the image is dense, it actually has to be surjective. But that's the latest theorem. So this is a rational map. So this is so in this expression, this is defined where f has no poles. So on C minus the set of poles of f. But we also have that phi is equal to 1 over f, comma 1, no, by just multiplying everything by f. And this is defined, where f has no zeros. So these two together define it everywhere. And now we want to see that the divisor of f is the pullback via this phi of a divisor of degree 0. And then the theorem shows it. So, note, so obviously x0, x1 are the homogeneous coordinates on P1. So then, if I take x1 divided by x0, this is a uniformizing parameter on P1 near the point 0 in A1, by which I mean 1, 0. And if I take x1, so this I could call x, if I take x1 divided by x0, which is, well, I don't actually need to put the name, x1 divided by x0 is, will instead be a uniformizing parameter near infinity. Is a uniformizing parameter on P1 near infinity, which I mean 0 is 1. If you just see, this is isomorphic to, here we have an A1 for which is the variable, and here we have another, near infinity, with another A1 for which this is the variable, and this is obviously the uniformizing parameter. And so if we take phi star of x1 divided by x0,
I think it should be x0 over x1 for the second for infinity.
Yeah, I mistyped it. Obviously, it is the inverse. So phi star of x1 divided by x0, this is by definition just, you divide by what the other is just f. No, this is what maps to x. Okay, and phi star of x0 divided by x1. So just if you compose this phi by x1 divided by x0, it means we take f divided by 1. No? And if you do it for the other one, you get 1 over f. So thus, if I take the phi star of 0, this is equal to the set of all zeros. So we take the set of all points where f is 0, and we take the zeros of that. That's the sum of all p in C with f of p is equal to 0, mu p of f. If we take phi star of infinity, this is in the same way the sum over all p in C, such that 1, so that if you want either f of p is equal to infinity, so that it's over mu p of 1 over f, which is the same as minus mu p of f, times the point velocity. And so we see that if we take the pullback of 0 minus infinity, this is equal to the sum over p in C, mu p of f times p equal to the divisor of f. And so this is a divisor of degree 0, and so this has the degree 0. Okay, so this is interesting. So in particular, we can define so the interesting part of the picture would pick 0 of C to be the divisors of degree 0 divided by the principal divisors. this is also often just called the Picard group. And so this is a very, and as I said before, this is a, I mean, we can just, so this is an important invariant of C. So this is so by definition, for a dominant morphism, P from X to C, and another one, say psi from Y to X, we have that if I take the composition psi star composed phi star will, from the, will just be equal to the composition, to the pullback by the composition phi composed with psi star from the divisors of Y to the divisors of C. So this is just clear from the definition. And so if, and obviously if you take, if the morphism is the identity, then it will be the identity. And so it follows that if X and C are isomorphic, then pick, so it's for the divisors, but also it preserves the pick 0. So I can put here pick 0. Then pick 0 of C is isomorphic to pick of X as the Billion groups. And now, so it's not clear by what I said, but this is really a quite fine invariant. So what one can show, if we have enough time, we will show is that if for instance have a curve of degree 3 in P2, then the so then the two such curves are, this Picard group is actually in 1-1 correspondence with the curve itself. And so it's, so we basically have that. And this, and more generally, if you have, well, I cannot explain it now.
The same for elliptic curves correspond to addition of elliptic curves?
Yeah, I mean, that's, yeah, that will be true. But anyway, so the group structure is this addition on the elliptic curve that one can define geometrically, but I'm not sure whether we will get there. I mean, if there's enough time, I will explain.
I have a question. So if we consider this association of a morphism to Picard group, so is it exact or not?
You mean, is it injective?
Yeah, I mean, considering it as a functor, is it exact or not? I mean, does it send, I'm not sure if this makes sense or not.
No, I think it doesn't. I mean, what do you mean, an exact sequence of curves? That doesn't seem to make sense.
If I have a, so my question is, can we use this to define some notion of homology or not?
I don't know. I don't see it. I mean, well, in some very abstract sense, you can. So, this, if you vaguely remember, I think you were even there. So there's this concept of something which is called motive, which which is some abstract thing which contains at the same time information about all possible cohomology theories of an algebraic variety in some abstract sense. And for curve, the corresponding motive actually is precisely described by the Picard pick 0. So in that sense, the universal cohomology thing that you associate to a curve is this thing. So in that sense, your statement is correct. But I don't know how, I mean, either you remembered that or it's a very surprising statement. because it's not. Okay.
Because
But
I
yeah.
don't remember that.
What?
I don't remember that.
Yeah.
I understood very
Yes.
little.
Yeah. But anyway, so in that sense, so there's some kind of general thing which is partially conjectural, which associates to every algebraic or every non-singular algebraic variety some kind of generalized cohomology, which is something very complicated. And in general, it's not very clear what this is, but for a curve, you see that it actually is this thing is also could also be called the Jacobian, and it is the Jacobian. So in that sense, you're right, but it's completely out of, it would be completely impossible to explain what that means. In addition, I don't know precisely myself what it means, but okay. I mean, I was at the same seminar, but anyway. Okay. So the first thing you want to show is something very simple. Namely, we want to show that this Picard group at least characterizes rational curves. So we can see from the Picard group when the curve is rational. That means when it's P1. So this is the. So we do this in some steps. So first we do something which we anyway will use several times in the future. Proposition. The curve C is rational. So priori, that would mean birational to P1. But as projective curves, if they're birational, they're isomorphic. It means it's isomorphic to P1 if and only if. So like this. There are 2 points. In the curve, which are linear equivalent. Okay. So, so let's prove it. If C is rational, so then it's isomorphic to P1, so we can assume that C is equal to 1. And so we just take, in this case it works, instead of there are, we can take any 2 points. So let P element in, so P equal to say AB, and Q equal to CD, be 2 points in P1, arbitrary. We put F equal to A times x0 minus B x1. I hope it's right. Yeah, I think so. C times x0 minus D. Yes, x1. And you work out immediately that this vanishes precisely at the point AB, this at the point CD. So it follows that the divisor of F is equal to P minus Q. And so P is linear equivalent to Q. So here we have a stronger statement. So if C is rational, then any 2 points are linear equivalent. So which is more than what is stated here. But now we do, so this was this direction. So in fact, if C is rational, any 2 points are linear equivalent. So this, in this direction, we have proven something stronger than we state here. Now, in the converse direction, we want power to see it using only the weaker statement. So now let C be a curve, and P and Q elements in C, such that so P different elements, obviously, otherwise with P is linearly equivalent to Q. You want to see that this implies that the curve is isomorphic to P1. Well, and this again we use this theorem we had before about the degree of maps, namely So this means there exists a function, a rational function exists an f in Kc such that the divisor of f is equal to p minus q. So thus f gives me a morphism from C to P1 in the same way as before, with, for instance, f to the minus 1 of 0 is equal to P with multiplicity 1, because that's what it says here. So, therefore, there's one point for which the pullback is, so there's one divisor, the 0 divisor, for which the degree of the, so not f to the minus 1 of 0, so let me say it again. I didn't say it so. Obviously f to minus 1 of 0 is 0, but what I meant is more if I take the f star of the divisor 0 on P1, this is equal to P with multiplicity 1. So thus it follows the degree of f is equal to 1. And now, what does this mean? It follows that if I look at the field extension Kc over K of P1, this is an algebraic field extension, this has degree 1. Because that's the definition of the degree of a morphism. But we know, if you have a field extension of degree 1, it's, the two fields are equal. So, I mean, it means that, so it means the image of Kp1 and Kc is equal to Kc, so the two fields are isomorphic. So it follows that Kc is isomorphic to Kp1, and we know that if the function fields are isomorphic, then the curves are birational. So thus it follows that C is birational to P1, and we know that any two projective curves which are birational are isomorphic. So it follows that C is isomorphic. Okay, so this shows this thing. But we use this theorem, that the degree is preserved, so it's not a triviality. Okay, so where am I? And now we want to use this to show this thing that I claimed, namely corollary a curve C is isomorphic to P1 if and only if the tick 0 of C just is 0. I mean, there's just one, the class of 0. Proof. If fix 0 of C is equal to 0, we can take any two. So we take two different points in C. So then it follows that P minus Q is a divisor, so is an element in div 0 of C. So if I take the class of this modulo linear equivalence, P minus Q, this is equal to 0 as a linear equivalence class. So it follows that P is linearly equivalent to Q. And by our proposition, it means that, so which direction do I do here? This is this direction. So we have assumed that the pK group of C is 0. Then we find 2 points, 2 different points which are linear equivalent. And so by the proposition, we deduce that the curve is rational. So conversely, So now we assume we are on P1, so let D be any divisor of degree 0. Say P1 plus PR minus Q1 minus QR in pick 0 of P1, where these PIs do not necessarily have to be different. So you could have some of them are equal. You know, where some of the PIs or QIs could coincide. No, I just so if it's P1 plus P1, it's 2P1. No, it's not so big. Okay. So then I can just then we know by our assumption that it's P1, any 2 points are linear equivalent. So then it follows that P1 is linear equivalent to Q1, P2 is linear equivalent to Q2, and so on. And thus it follows that D is linear equivalent to 0. No, because there's some F which does this, some F1, some F2, and the product of the Fi will make these D be linear equivalent to 0. Okay, so that's that. Now I want to okay, so we haven't seen much about this pick 0, but the one thing that we can see that it distinguishes P1 from any other curve. Now, strictly speaking, in the moment we don't know whether there's any other curve. No, we have not shown that not every non-singular curve is isomorphic to P1. That could in theory be so. But I mean, we will see, if I have time later, that there are many other curves. I mean, infinitely many different isomorphism classes. In fact, it's much more complicated. Okay. But at least so we can distinguish P1 from anything else.
So I have a question. Is any group can be realized as a Picardy group? Or what kind of groups are?
No, I mean, first the groups are Hegelian. No?
Yeah, sure.
And you know, here, I mean, no, in some sense, not at all, because so you mean now, so let's just talk about pick 0. So the Picard group is always, you have the degree, which is just Z, no? And so you have the pick 0 is the kernel of this thing, which goes to Z. So the Z is anyway trivial, is always the same. You have pick 0. And so the Picard group always will be what is called an algebraic variety. So it's in a net, so will be an algebraic group. So it will always, so say we work over the complex numbers. Then the Picard group will can always write this as C to the n divided by some letters. So it's always, you know, and and in fact, you can prove that it's always an algebraic variety itself in a natural way. And certainly, so in particular, you know, you don't have, if the group is not one, it's not just consists not of one element, it's certainly not finite. In fact, it's over the complex numbers it has, you know, it's a positive dimensional thing. But anyway, it will always be, so, well, it will always be some such torus, C to the n divided by lattice. So topologically, over the complex numbers, it is, you know, like a higher dimensional torus. For instance, for an elliptic curve, it actually is equal to, for a curve of genus 1, it actually would be equal to the curve. And so the elliptic curve, a curve of genus 1 actually of, or say a cubic, is by itself a torus. And the Picard group will also be a torus, and as a group, it's also a torus. No? Anyway, but this is obviously I don't have the means to do this now. So now I want to talk about the degree of the curve and Bezout's theorem, which answers partially your question. Oh. So I want to say what I mean by the degree of a curve, and I want to prove a version of Bezout's theorem for curves. So first I want to say what, so part of what we do here is we have introduced these divisors. So until now we have introduced, first we've introduced general divisors. Now we got this Picard group and all this stuff by introducing divisors associated to rational functions, which are the principal divisors. Now we want to associate divisors to, so if you have projective curves, it lives somewhere in projective space, you want to associate the divisor to a polynomial in the ambient projective space. And then this gives us, if one looks at carefully what it does, it gives us Bezout's theorem. Okay, and also, so let's see how that works. So, and then later, I don't know when, we will also associate divisors to differential forms. And this then gives us something, some even more subtle structure and more interesting results. So, for definition. So, we take a curve in Pn, a smooth projective curve, but now I want to view it to lie in Pn. And I take a polynomial living on this projective space, but it should not vanish on C. Okay. So then I can associate the divisor to F, to this polynomial. So the divisor of F, and with my lack of fantasy, I call it div of F. No? Of F is defined as follows. So let's take any point. So we take for any point P in the curve C. So I write down the coordinates of the point. So it's P0, Pn in C. It will lie in one of these open subsets here, one of the UIs. Yeah? So choose an I with Pi different from 0. And I can put F of say, yeah, it's stupid. Well, I could just say, I just write this as a big problem with the notation, but it's not. So maybe I can just say and so if Pi is different from 0, we can assume that Pi is equal to 1. So make normalize such that Pi is equal to 1. After all, it's a point of projective space. Then we put f of x0. We take away the xi until xn. We define this to be this polynomial evaluated as x0. We put the ith variable equal to 1 until xn. So we just have, what it really means, we have dehomogenized. The correct way to do it, if one doesn't want to do this, that we have to take x0 divided by xi until xn divided by xi. In the way we had done it, you have done it in some homework. So this is some polynomial in these variables. And it's also, these now, no, I have to be more, I want to be more careful. Let me do it correctly. No, it's not good to cheat these trivial things. So we put the f of, say, I maybe just call it y0, and then yi. No, I just try f of x0 divided by xi until, so this one we don't take, it doesn't depend on this, until xn divided by xi. So we I don't exactly. So let's just look at this. So we consider f of x0 divided by xi, and so here we have 1 xn divided by xi. So this is now these xi's. These are now rational functions. No, there's a quotient of two polynomials there. So this is a rational function. And so we can therefore say we put nu p of f to be equal to nu p of f, nu p of f of x0 divided by xi, 1 xn divided by xi. So this is a rational function, so it has a multiplicity. We can just do this. So what it just means is, this is a polynomial. If we restrict it to a chart, it is a polynomial in the variables on the corresponding affine space. This is a rational function, and I can look to which order that vanishes. And then check this is independent of I. So if obviously there could be many coordinates here which are non-zero, but you will get the same multiplicity.
And just skeptical if it is a rational map.
Rational function.
Yeah, because for example, if we take f to be x0, x1, so when we divide and assume that our point is in the second chart, so when we divide by x1, we get just x0.
What? No.
I mean, because there is no assumption about f, so we are just taking an arbitrary polynomial, and we are dividing by one of its variables. Why should be a homogeneous degree?
No, it's not homogeneous. It's not. So.
I mean, why it should be rational function of the curve?
x0 divided by xi is a rational function.
Yes.
And I have a polynomial in rational functions. That's a rational function.
Yes. Okay.
No, I mean that's true. No.
Yes, true, but
obviously you can also try to work it out by yourself, so, I mean, it is, because you write some expression in a quotient like that, so it will always, the degree in the numerator and denominator will always be the same, because you have it already, each single term has that property. But at any rate, you can easily show that the polynomial in rational functions is a rational function. After all, because a rational function is a, okay. So this is independent of I, so this is kind of an exercise. So then the divisor of f is, div of f equal to the sum over all p and c, the multiplicity of f times p. So notice that, so in one chart it's a rational function. If you look at another chart, it is another rational function. So you cannot, you do not know that the degree of this has to be 0. It usually won't. In fact, you will see in a moment what the degree is. So what we can see is, that the support of the divisor of f will be the set of all points where the zero set of f, where f is 0, which lie on C. So this will be equal to the zero set of f intersect C. Because this multiplicity is non-zero if and only if f of p is non-zero. And it's 0 if and only if f of p. So this multiplicity is non-zero if and only if f of p is 0. So this thing, and obviously the divisor of f is effective. So this I look at the point. If if a point lies in the intersection of these, it will be 0. And if it does not lie in the intersection of the zero set of f and c, then this thing will be non-zero. So in each case, this number is either 0 or positive. So this will be an effective divisor, which is supported here. So that's div f counts is sum of the points of the zero set of f intersected C with positive multiplicities. Okay. So in particular, the degree of this will always be bigger or equal to 0, and in fact, if these things intersect at all, the degree will be positive. And we can also see, so if I take two polynomials, so if f and g are polynomials in kx1 to kx0 to xn, both of the same degree, which both do not lie in the idea of C, then if I take the divisor of f minus the divisor of g, you can easily check that this is just the divisor of the rational function f divided by g. No, because so this is where this vanishes. So this tells you precisely where f vanishes. The divisor of this is precisely where f vanishes with the multiplicity with which it vanishes. F divided by g gives you the corresponding thing here. If you just work it out, it's almost by definition that this is equal. So thus it follows that for any two polynomials of the same degree, these two, the corresponding divisors are linear equivalent. So thus, for any two, so let's say f g in k x0 xn d, the divisor of f is linear equivalent to the divisor of g. In particular, they have the same degree. Because we have seen that linear equivalent means that the difference is a principal divisor. The principal divisor has degree 0. So if two things are linear equivalent, they have the same degree. So now I can define what the degree of a curve is. I mean, I expect you imagine, for a curve in P2, the degree should be the degree of the equation of the curve. But what now if the curve instead lies in a higher dimensional projective space? So let the degree of curve C in Pn is the degree of the divisor of H for H a polynomial of degree 1. So I have a linear form which the zeros, we take the divisor of that. So intuitively this means the zero set of this thing is a hyperplane, and so the degree is the number of intersection points of C with the general hyperplane. Or for any hyperplane, it's the number of intersection points with the hyperplane counted with multiplicities. No, with positive multiplicities according to this. So this number of intersection points C intersection is the zero of H counted with positive multiplicities. And now, on the other hand, as I just said, it seems to be obvious what should be the degree of a curve in P2. No, if the ideal of the curve is generated by a polynomial of degree d, then we would want that the degree of the curve is d. So we should see that this coincides with this definition. So this is the following proposition. Let C be the zero set of some polynomial f in Pd, so such that Pn maybe, such that actually we want that the idea of C is actually generated by f, and then f has degree d. I mean homogeneous of degree d, then the degree of C, according to the definition we just gave, is equal to the degree of f. Okay, so that means, if you wish, it's a special case of Bezout's theorem. The number of intersection points of a curve with a line is equal to the degree of the curve, I mean of the polynomial defining the curve. So let's see whether we can prove that. Hope I don't start to run out of unaddressed responses. So that maybe, so we know that, well, okay, that is good. So let H be linear polynomial. So x1, x2 of linear form. So and for simplicity, assume that all the intersection points of these two lie just in one chart. We can arrange that, you know, because they are only finitely many intersection points, and we could make a linear transformation. So So therefore there will be some hyperplane which does not contain any of the intersection points, and then we could make a projective linear transformation which makes that the line at infinity. So we can assume that that these points lie in U1, in U0. So all points of C intersected H lie in U0. So the set of all, so that means A0. So which we identify with A2. So the first chart, so I mean it's just side to U0, so that means A0, A1, A2, and B2, such that A0 is not 0. So we write f of xy as so f was our polynomial defining curve as f of one x1 divided by 0 x2 divided by x0, so we have that x is equal to x1 divided by x0 and y is equal to x2 divided by x0. Okay, so we just write it in this form, in this chart, and we can, by further linear transformation, we can assume that this h is just, this polynomial is just a polynomial y. And we just make a linear transformation so that this becomes y. We can assume h is equal to, originally it is equal to x2, so the zero set of it is the zero set of y. So that means if I take C intersected the zero set of h, this is just the zero set of this f and y. Okay. So now let's take one of these intersection points. So let P be a point in C intersected CH, I mean in this. Then what is mu P? We want to know what the multiplicity of this y is. So mu P of H is just mu P of this function y. So this means, so if the multiplicity of this is a certain number, it means it lies in the maximal ideal to that power. No? And so this means that if I take, I claim this is the dimension over K of the local ring of C at P divided by y. No? So we have, so let's just see. Let me just say again. So if the multiplicity of this means that we can write as y equal to t to the mu of p times the unit. So which is the same as saying that y is an element in the maximal ideal at p to the power mu of p. And you can easily see that if you take O of x modulo mp, this is k, so it has dimension 1. Take mp modulo mp squared, this has dimension 1, and so for all other ones. So it follows that if this thing lies in the maximal ideal to this power, it means the dimension of this quotient is this. Now, this is the same as taking the local ring of A2 at P and dividing it by the class of f and y. No, we just have, this is the same thing. And now we can exchange the role of f and y. So this is the same as the dimension of the local ring at, on the zero set of y. Let me just, so if you look at this, so we can take this thing divided by y and divide it by the class of f. So this is the same as so if we take, so this is, we take k, right, let me just, so if we take the local ring, if we divide by y, so the zero set of y is just, the y-axis. So this would be the local ring of c of y at p, the dimension of this, divided by f. And so what does this mean? So this is just nu p of f on this thing. But what does this mean? So this z of y is just a1, and we have, this is just the order of vanishing at the point, so if p, so if p, so we have here the point, obviously, we know now the second coordinate is 0, so if p is equal to a, comma 0, then this number, p of f, is just the order of vanishing of f of x, comma 0 at a. No, just view it as polynomial as one variable less. We take the order of vanishing at that. And what is this is just a polynomial in one variable. We know what this is, and we know this polynomial has still the same degree as before. No, f of x, comma 0 still has degree d. Because otherwise the whole thing would have had to be divisible by this z, which we have excluded, by x0. So thus the sum over, so the sum of all the multiplicities, the orders of vanishing at all the points of polynomial of degree d, we know, is d. So thus the sum over all p, over all a, in all points a with f of x of a 0 to 0 of the multiplicity of vanishing of the vanishing of f of x0 at a is equal to the degree of f, which is d. Okay. So we somehow, so what this means, so how we do it here, we somehow exchange the role of the curve and the hyperplane. So the intersection number is the same, whether we think of the line as the curve or whether we think of the curve as the curve. And then it's really just the order of vanishing. So if you're on a line, we're actually on a1, and our hyperplane just becomes a polynomial of degree d, and we just look at the sum of the order of vanishing. Okay, so this proves this. And then finally, we can state, or Piso's theorem, I mean, slightly skimmed down version. So first, we can do something in general, so let C in Pn be a curve of degree d, where now the degree d means that you know, the number of intersection points with the hyperplane, then and let f so be a polynomial of degree e, which does not range on the whole of the curve, then the degree of the divisor of f, I mean obviously on C, is d times e. And in particular this holds in case the curve is in P2, which is the usual Bézieux theorem. So in particular, if C is in P2, is a curve, which means non-singular, with the ideal of C is equal to F, maybe I call it now F, G, with the degree of G is equal to D, and then we have that the degree, and so, okay, and again F is a point, F is in kx0 to xn of degree E, then again the degree of the divisor of F on this curve C is D times C. And so, so that means that, so in other words, the number of intersection points of C with a general with either any line or a hyperplane, a line in case P2, or a hyperplane is D times E. So in particular, if we have two curves in P2, which have degrees D and E, then the intersection points counted with multiplicity are D times E of them. Okay, and that's the statement of Bézieux's theorem, and it holds more general with this notion of degree for any dimension. But you have to intersect with a hyperplane. And so the proof is not very, I mean, we have basically proven it already, and there's nothing to prove, almost, because it's just a question of linear equivalence. So proof 1. So let H be a polynomial of degree 1. Which does not range on our curve C. Then, obviously, I can take this F and divide it by H to the D. This is a rational function on C. No? You have a quotient, so I take the classes of these and I take the quotient. This is a rational function on C. So therefore, thus we have the degree of the divisor of f is equal to the degree of the divisor of h to the d, which is equal to d times the degree of the divisor of h, no, because it's just obviously adds up, which is equal to d times the degree of c by definition. And the second statement is just a special case. It's just a special case. So 2 follows from 1. Because the degree of our curve C is, as you have seen, equal to the number D. No, this was actually, we had actually, it's a bit, there I called the degree of this thing was E, so maybe I should do it correctly. So this is E, this is E, and this is E, and the degree of C was D. If we look at what I wrote. Okay. So much for this. This is the Bezout theorem. I mean, strictly speaking, the general Bezout theorem is slightly more general because here we are assuming that at least one of the two curves is non-singular. There's a notion where you can make this, you can generalize the statement where both, both the zero set of G and the zero set of F could be both singular. And then the definition of the intersection multiplicity is more complicated. You can't define it in terms of a uniformizing parameter like we do here. But okay, so
does this use blue ones?
No. No, you can do directly in terms of it was implicit here. So the intersect you have to define what the intersection multiplicity at a point is. And for this it's actually what, so you can again assume that your point lies in A2 by making a chart, and you have then the two equations, and then the intersection multiplicity at P of the two polynomials would then be equal, you take the dimension as a k-vector space of the local ring of AT of A2, or the local ring of A2 at the point divided by the ideal terminated by Ng, where these are the corresponding defined things. So I have shown here in the proof that in our special case this is the same. I've used it because in order to exchange the role of F and G. Because the advantage of this obviously is that it's symmetric in F and G. Okay, but this is, for instance, in Fulton's book you find
he first do it axiomatically, and then he want to show that such a function exists.
And then he defines it in this. Yeah. It's
the most obscure way to do things.
Okay, so let me see what I can sensibly do. A bit. I wanted to briefly. Let me briefly talk about, I don't know whether we have time to actually. Yeah, so I wanted to use this thing. The only thing is that maybe I can very briefly do this. So there's one important the question is whether it's sensible to introduce something when if it later then I don't have the time to actually use it. So that's an interesting question. On the other hand, it's an important thing, and you would certainly see it in some form in the future. So let me just very briefly do it. So we want to look at the spaces L of D. So we want to use a divisor to define a certain vector space of rational functions. This actually later, if one has the time, which we won't, all the morphisms between curves would be defined using these rational functions, which is obtained in this way, so that you can use divisors to define morphisms. But we are not going to look at this, but at least let me see how it goes. So to divisor D and C, we associate, so I write D equal to say sum P AP times P. We associate the set of function that so L of D the space of F in KC. So maybe I really make it as definition. Instead of saying it first, the set of all F in KC such that if I take the divisor of F plus D, this is effective. So I write it like this. This means it's effective, all the coefficients are non-negative. So that means if, so to just understand what it means, if, so just write it in, so A of P, to write it properly, is the set of all F in GC, such that F, so first like this, such that F divisor of F plus D is effective, and then we add 0 to it. So here some of these numbers might be positive, some of these might be negative. So what does it mean that? So it means after adding the divisor of F, all the coefficients should be positive, non-negative. So that means if the number here is positive, then we allow F to have poles of certain order there. Namely, if here AP is -5, then F is allowed to have a pole of order 5 at this point. And if AP is negative, then they require F to vanish to that order at the point. Okay? So in other words, if we look at this, we prescribe both poles. So we prescribe zeros and allow poles by using this D. Okay? So note this LD is a K-vector space. So which is obviously it's contained in KC. So it's a sub K-vector space of KC. Namely, if A is in K, I mean, if I multiply something by 0, it becomes 0, so it still lies there. But if A is in K without 0, then obviously the divisor of A times F is the divisor of F. So therefore, if F is in LD, then AF is in LD and vice versa. And if F and G are in LD, then we know, then for all P in C, we have that the multiplicity at P of F plus G, this was one of the things that we had seen, is bigger or equal to the minimum of the multiplicities of F at P and the multiplicity of G at P. So thus it follows that if F and G are both in LD, so that means for each of them the multiplicity at every point is bigger than minus the corresponding multiplicity here, then it follows that F plus G also is in LD. So therefore LD is a vector space, a K vector space. Okay. And now I want to see a few things and then I stop. I don't know, maybe that's, maybe I could try to sketch it. So this was this. So one thing, so we have a couple of lemmas. So if the degree of D is smaller than 0, then it follows that this vector space is the 0 vector space. And if the degree of the divisor is 0 and the vector space is not 0, then it follows that D is linear equivalent to 0. Okay, so the first one is kind of clear. So if E, so if F is an element in LD, then the divisor of F plus the divisor plus D is an effective divisor. All the coefficients are positive. So in particular, the degree of the divisor of F plus D is bigger or equal to 0, but this has degree 0. And so the degree adds up, so this is a contradiction, so the degree of D is smaller. So this is not possible, obviously only when F is not 0, otherwise this whole thing doesn't make sense. And the second is also quite simple. So let's assume the degree is D is 0 and L of D is non-zero. That means there exists an F in KC, which is not 0, such that if I take the divisor, D plus the divisor of F, that this has non-negative coefficients everywhere. So as we also know that the degree of D plus the divisor of F is still 0. So all the coefficients are non-negative and the sum of their coefficients is 0. So it follows all the coefficients are 0. It follows that D plus the divisor of F is actually the 0 divisor. So therefore, D is linear equivalent to 0. And maybe, okay. So this is an easy lemma. And where am I? Yeah, I wanted to bring this to its natural close. Maybe I will just leave this. Next one is an exercise and then give one example. So, lemma. So, if I have two divisors, D, which are linear equivalent to E, then it follows that L of D is isomorphic as a vector space to L of E. Okay? And let me just say what it means is, so if so these are linear equivalents, so if I have a function f such that the divisor of f is equal to d minus e, then you can just see, is it the right way around? Or maybe e minus d. Then I just claim, and you can check this, we have a, so if I take, so for G in LD, we get that f times g is in LE and vice versa. So multiplication by f is a map from LV to LE, and the inverse is inverse multiplication by 1. Okay, so I haven't done this in detail, but it's really a simple exercise. And now I wanted to compute this at least in one single case. And this is when you're on P1. Yeah, sample. So I call the definition, this is a vector space, we're interested in the dimensions, so we call L of D, small l of D is equal to the dimension over K of L of D. And now in the case of P1, we want to compute L of D for all divisors. This is an example. So if P is a point in P1, then we know that P is linear equivalent to the point infinity, equal to 0, 1 in P1, because any 2 points in P1 are linear equivalent. So thus, any divisor D is linear equivalent to the degree of D times infinity. Okay? Of course it does. So now let's see, we want to compute these, what this L of D is for, what we get. So let's look therefore what we get. So let's compute L of D times infinity. All right, yeah. So we have again the coordinates on P1, the co-homogeneous coordinate x0, x1, and then on the A1 we have x1 divided by x0. Dx, and then we know that the function field of P1 is just the field of rational functions in X. So just let H, you can write as f of x divided by g of x, be an element in this. And we can assume that f and g have no common divisor. So I can split these into linear factors, because they're polynomials in one variables. I can assume they have no common zeros. So assume f and g have no. So first, let me just say one more thing. So first, if d is smaller than 0, we know by what we said before that L of d is 0. We know in general that L of d times infinity is equal to 0. We just prove this for any divisor on any curve. So we assume d bigger equal to 0, and so we can assume that f and g are relatively prime. So that means they have also no common zeros. So any zero of g would be a pole of would be a pole of h, in A1. But we don't allow for poles here, so we know that g must be constant, must be degree 0. So we know, so any 0 of G would be the pole of H, thus G has degree 1. Degree 0. It's a constant. Oh, let me now stop though. Okay, I'm almost done. No, otherwise it would give me a pole of H. So, so let now say n be the degree of H. So now the uniformizing parameter at infinity is 1 over x. No, on P1, the local, no, you have the coordinate, on the one chart the coordinate is x, on the other coordinate is x0 divided by x1, which is 1 over x. So the uniformizing is 1 over x, which I call z. Thus, we can write h. So thus h is a polynomial, sum I equals 0 to n, ai times 1 over z to the I. It's just, h is just f, no? It's just f of 1, so h of x is equal, I can put g equal to 1, so f of x, and fx is 1 over z, it's just like this. So, okay, so you can see, so I can write this is equal to z to the n times sum I equals 0 to n ai z to the minus n, z to the n minus I. So with the ai here, so if this is the, so therefore, if the degree of the original polynomial f was, so ai is non-zero, because the degree of, I take n to be the degree of this. So then we see that this thing starts with an element, non-zero element in k, so this is a unit. So I have z to the minus n times a unit. So if h, which is f, has degree n, then it's z to the minus n times a unit. So it follows that the multiplicity at infinity is equal of h is equal to minus n. Okay. So therefore, we want that this number is small. This minus, that d minus n is bigger than equal to 0. So it means d must be smaller equal to n. So thus we find that L of d times infinity is equal to the set of all the f in kx such that the degree of f is smaller or equal to d. And so in particular we can compute and so we are here in P1, so it's polynomials in one variable, so it follows that L of D is equal to the maximum of 0 and the degree of D plus 1. Because the number of polynomials of degree D, of the degree smaller or equal to D, the dimension of that is D plus 1, and we find this. So in this one case, we have computed this thing. Okay, maybe I will stop here. I went sufficiently over time, although